Okay, so today's discussion will be around integrating our AutoDRIVE simulator with OpenCAV vehicle, so that AutoDRIVE now like supports full-scale CAV simulation as well. So in the last technical discussion, we discussed what AutoDRIVE ecosystem is. Just to brief about it, it is uh, the idea is to have a hardware test bed, a software simulator which acts as a digital twin of the test bed, and a separate dev kit which now has different APIs to connect with both the test bed and the simulator. We are also aware of what the open CAV ecosystem is. So it is the full-scale Chrysler Pacifica vehicle, which is fully integrated, but it's not just the vehicle. It's more than just the vehicle. It has other components to it, which make it an ecosystem rather than just a simple autonomous vehicle. And what we are talking about today is about integrating the two ecosystems together to have a common tool chain for development deployment as well as use it for similar kind of applications. So AutoDrive Simulator earlier we had a scaled vehicle called Nigel, which was 1:14 scale vehicle, which was primarily meant for in-lab research. But now with OpenCAV in the simulator, we have a full-scale vehicle which is intended for proving ground research. The first part of developing the vehicle model for the visualization is the materials, which have to be photorealistic. So we made use of high definition render pipeline from Unity and defined the vehicles in that rendering pipeline as well as the shaders. The surface rendering was also taken care of by defining appropriate opaque and transparent materials, and the textures and decals were used with appropriate UV mapping to wrap the Pacifica texture around the OpenCAV texture around the Pacifica vehicle. So I'm not sure how we will be able to do this in like softwares other than Unity, because like currently we have used Unity's rendering pipeline to project those decals onto the vehicle. Uh, Another thing that HDRP offers is like different material properties. So we have standard materials which can be adjusted for their metallicness or smoothness. We have materials with subsurface scattering, which is basically simulating the light penetrating through translucent objects. Uh, we have anisotropy, which means the material will change its properties based on the direction or orientation that we are viewing it from. So something like galvanized aluminum, which will look shiny from one side and like rough from the other side, something like that. We have iridescence, which basically simulates the iridescent effect, as it's called. It look basically it is like a glass. When you view it from a like oblique angle, it looks a little bit like rainbowish. So that is that iridescence effect. We have specular color and specular reflections taken care of. We also have translucent materials, which are thickness aware subsurface scattering materials. And lastly, we have emissive materials, which simulate emitting of light emitting objects. So to talk more about lights, first is of course the emissive materials. So the vehicle has emissive materials currently defined in the instrument cluster. We'll be showing live demo of this after the presentation. So we have, or it is actually a better idea to do it live. So let me just open the simulator. So we were discussing about different materials. So I'll just quickly show one or two of the sample cases. So the iridescence effect, as I said, if you see the like glass from a side viewing angle, you can see the iridescence effect. Similarly, the translucent objects and transparent objects are basically rendered according to the respective materials. So that is one thing. Then we discussed about the decals, which you can see being projected on top of the Chrysler Pacifica from all the sides. And then we are talking about lights. So we have emissive materials in the instrumentation cluster and the light bulbs and other emissive surfaces of the vehicle. So one thing I know of is the parking lights of the vehicle, which have this. So as you can see, this is an emissive material, and we have one in the instrument cluster as well. Then we have live ray casting, which can be like in real time or partially baked or fully baked. So we have two, like in this particular vehicle, we have used two kinds of ray casting methods. One is spotlight and other is focus light. So spotlights are used for things like tail lights or indicators, which are emitting light in a point fashion. So if I just show this, this is what point light is. Even the brake lights are point lights. But if you now go to the front, you have again point lights in the indicators. But then when I say spotlights, you have spotlights in your headlights, which basically project cones and like do like real-time raycasting to define which area of the environment is lit. So we are also using post-processing for like scene lighting. So this includes ambient occlusion, auto exposure of the cameras that are rendering on the front end, the bloom effect, which is basically when you have light on a surface which is having high albedos, you will have a bloom effect. You have color grading to like match color all across the screen, and you have screen space reflections, which basically, as you can see on the vehicle, reflect at different angles onto the screen, the metallic properties and other things. And apart from this, the vehicle itself we have modeled with lights and indicators. So it has headlights in high and low beams, which I just demonstrated. So this is low beam with projector lamps, and then this is the high beam with projector lamps as well as the main headlamps of the vehicle. We have tail lights which are off, dim or bright automatically based on, so when the headlights are enabled, they are like in dim position, and when you hit brakes, they are brightened. We have turn indicators for left, right, and hazard indicators. So this is left indicator, this is right indicator, and this is the hazard indicator from both front and the rear of the vehicle. Then we have reverse indicators, which are automatically triggered if the vehicle is driving in the reverse direction. And we have brake indicator, which I demonstrated here on the vehicle, top rear. And we also have fog lights, so, which basically have high range and low low high range and low zone of the focus. So that was about the lights. Next, we have vehicle dynamics parameters. So we have split this into different sections. So first, we'll talk about rigid body kinematics and dynamics. So the vehicle's mass and drag. So this drag can be like added as a static constant drag parameter, but we have modeled it as a variable drag based on the velocity of the vehicle for both angular and linear and angular motions. We are using interpolation for collision detection, and as you can see from the presentation itself, this green highlight that you can see on top of the vehicle is the collision mesh. And we have modeled the Ackermann steering mechanism, meaning the left and right wheels won't turn equally. They will turn in the Ackermann steering geometry fashion. And the dynamics also covers understeer and oversteer. So if I were to demonstrate that. You might hear some unpleasant noises because I will be using the keyboard and then turning the vehicle. So I'll just brake the vehicle. Now if you see, the vehicle's turning radius is in kinematic fashion is just this much. But now if I increase the velocity, it will go in an understeer maneuver. I'll come to that. So we have like next thing is suspension dynamics. So we are using a sprung mass representation where the sprung mass is defined by the upper like mesh collider of the body of the vehicle, and the unsprung mass is defined by the four wheels which have their independent masses. I think it's 25 kg. We are like modeling the travel, natural frequency damping ratio, and force shift of the suspensions as well. And we are also actually modeling the anti-roll bar, which we have defined in the rear of the vehicle right now. So I'll just quickly show those aspects. So here you can see the script. So the script is a C sharp script, which is which basically goes through defining all the dynamics equations and things like that. Oh, this is camera control. Yeah, so this is the script which defines all the vehicle dynamics and functions, equations, other things. And here basically you get an idea of the parameters that we are using. So we are actually using torque curves of the engine or the motor and the gear shift ratios. These parameters were actually taken from Chrysler Pacifica spec sheet. We are also modeling the speeds at which the gear shifts occur, as well as the engine RPMs at which they should occur in automatic transmission. We are modeling to talk about suspension specifically. We are here are the parameters that you can tune for suspensions, and here is the anti-roll bar script attached, where you have the rear two wheels with an anti-roll coefficient of 5000. So next is the powertrain dynamics. So we have different drive types: forward wheel drive, front wheel drive, rear wheel drive, and all wheel drive. For Pacifica, we are using front wheel drive, and that's why you saw the understeer performance. We have engine RPM and the torque curve, which I just showed, and you can also see here. We also have the transmission and gear ratios modeled. So this is the gear ratio plot, and transmission I'll be talking about. And we have also modeled differential split and torque drop at differentials. So if you see here, uh, these are all the parameters that define the transmission. So we have final drive ratios for left and right, differential split. We have this is the engine maximum gear change RPM and minimum gear change RPM. So this will be used for upshifting or downshifting the gear in auto transmission. And these are the other few parameters which are so these are engine RPM is like calculated on the fly, and these are other few parameters which basically are used for modeling the powertrain. So the next thing is actuator dynamics. So the vehicle has throttle, brake, handbrake, and steering actuators. So yeah, we talked about the different actuators. Now we have also modeled the response delays, the deadbands, and saturation limits of each of the actuators. Coming to tire dynamics, we have defined tire models, as you can see here, with extremum and asymptote kind of model, which kind of mimics the tire profile as we have observed. And we have also modeled the stiffness and friction of the tires and the road surfaces with physical materials. And we as Dr. Krovi mentioned, we have also modeled tire effects with skid trails, smoke, and audio. So the screeching sound when you hit the brakes too hard. So let's try once more.
What do you think are the minimum specs you would require for your simulator?
So actually this simulator has different graphics qualities, low, medium, and high. So low qualities are actually targeted towards low spec PCs or workstations. Right now I'm just showing high or ultra. So to demonstrate the difference between handbrake and combination braking. So this is actually the engine sound, which in this case is an electric motor. So that's why you're hearing it humming sound. So if I drive this now and brake it with a combi brake, all the wheels are locked. But now if I hit the hand brakes, only the rear wheels will be locked. So since I'm using keyboard, you will be hearing a lot of if I hit the, so you can see the front wheel still rolling, but the rear wheel screeching. So that was about dynamics overview. Sensor suite, we have more we have data from the telemetry of the vehicle itself and the simulator. So we have time, real time factor, and simulation time that is live here. So we have the simulation time and the frame rate, which is currently dropped very low because I'm running very parallel things on this same machine. So apart from that, in telemetry, we have the driving mode and the gear shift of the vehicle. So currently it's in manual mode with drive selected. And we also have the speed of the vehicle in meters per second. We have throttle, brake, handbrake, and steering feedbacks. We have also modeled the GNSS and IMU. Currently it's in perfect condition, but through APIs we can add noise or other disturbances that we want. So the GNSS is simulated simply using the rigid body transform of the vehicle, and it's defined at the rear axle center. The IMU is scripted to calculate the orientation in both Euler angle representation as well as Cottonian representation, the angular velocity and the linear acceleration of the vehicle. Cameras we have also modeled to actually be as close to the Mako cameras that the real vehicle has by setting their focal length and sensor size in simulation. And we are also using post-processing effects to now have realistic rendering on the from the cameras. So just to demonstrate quickly the cameras. So as you can see, the two cameras clearly have different focal length. In one, you can see the crossing quite near, and in the other, you can see it further away. So yesterday we went on we tested the real vehicle out for today's demo, and we found that the GNSS and the IMU are actually relaying their information to the base vehicle frame, which is basically the rear axle of the vehicle. Center of the rear axle. Yeah. And we can change any of that parameters if we later find out that it is not what the real system is doing. We can come and change them in the simulator. So that was about the sensor suite and the 3D LiDAR we are currently working. We have a 2D LiDAR already for the scaled vehicle. So now we'll talk about some of the extended features. So we have a first person's view with the detailed interior of the vehicles with all the materials. We also have an animated steering wheel, which I'm not sure if anyone of you noticed from exterior of the vehicle right now, with a steering ratio of I guess 16.2, which is the one of the Pacifica. And we also have a live instrument cluster, which currently supports the speed and the gear shift. So let me just quickly demo about that. Hard work. That's the right term.
Do you have any basis? You got a model of the interior and
So there are images from interior of the Pacifica or the product manuals, things like that. Distracted driving. So if you closely notice, the steering delay is also modeled. So even if I press a digital key, the steering is not going directly to the full position. It's changing gradually. And this is not just in the inside of the vehicle, even in the outside, you will see that it moves with a delay.
This is one thing. So you should show the vehicle from the outside view.
Yes.
You're doing your little thing. You should also show the vehicle from the inside view and say that we have the ability to put sensors everywhere
Right.
that then monitor either the passenger and passenger distraction,
Yes.
right, as well as the passenger interaction with the console.
So actually this view was actually meant for that. So haptic teleoperation which Partha is doing, or any other teleoperation, and driver in the loop kind of simulation, testing, verification, validation, those kind of efforts, which I guess Dr. Pravi mentioned, driver attention, driver distraction, things like that can also be like studied. So yeah, as I was talking, the steering, another thing that we have modeled is based like in the real vehicle, based on the velocity of the vehicle, the sense like will vary. So if you have the vehicle standing still, I'll just take it a little bit back so that everyone can see it in the light. So if it's standing still and I steer it full, it won't go at that rate at which it would go if it was moving at a high velocity. So if I will, you can also see, by the way, the steering inside moving from this angle. So if I just let it go, it will slowly come back to its original like 0 position. But if the vehicle is actually driving, then it will come back at a much faster rate. So the next thing is the data recording. So we have a one-click data logging functionality within the simulator, which records time synchronized data. So a simple representation here is like, this is the record data button, which brings up a pop-up for like selecting the location where you want to store the data. And then the data is stored in two like different ways. One is a CSV, which contains all the telemetry information and like sensor readings, which can be in the form of numbers, and we save the camera images separately, so that is not and all of this is time synchronized and saved parallelly. And to make it optimal or efficient, I wouldn't say optimal, but yeah, to make it efficient, what we do is we save some of the data online, which is like inertial parameters and things like that. So if I just want to show a quick demo, so I'll just create a new directory first. It's in B colon. I'll select the folder. And now if I click the button or hit R, the data is recording. Now I can drive the vehicle around, and all the sensor readings, all the telemetry data is being recorded at the back end. And once I hit the button again, it will start saving the data. So all the other telemetry data, inertial data, sensor data, it's stored initially, but it's now storing the camera images since they are a little bit heavy. So we have offloaded this computation. We update we store the transform of the vehicle while we were recording the data. We move the vehicle there, and then we capture the camera frames. Small number, and that will basically cause. So this is manual mode. If it's in autonomous mode, your autonomous algorithm will suffer just because you are recording data, and that is not what we want. So this is a way that we have like made it efficient. Now these are the two key things that like a lot of you had questions about. So first is backend scripting. So with AutoDRIVE Simulator, you can script all the dynamics, behaviors, graphics, like the front end rendering behaviors, shaders, even if you are like expert in that, to define all the functions, features. Like you can actually add more functions and features to the simulator, and this is all possible. I'm not sure how many like pre-packaged simulators out there support this, but since this is an open source simulator, you can actually go and like do all of these things on your own. Another thing is the API support. So currently we have APIs run like set up for ROS, Python, and C++, and we are working on setting APIs for MATLAB Simulink workflow, as well as ROS2 and AutoWare. So that was pretty much about the presentation. Just a couple of things that we missed out in the presentation, and since we have modeled them, just would like to show them. So first one is the light delay, as I was talking about. So we have modeled the capacitive delay for the headlights, So if I turn them on and then turn them off, they won't go off immediately. They will have a like minute delay, but it's there. You can see them smoothly going out. That's also for the high beams. That is one thing, and the second thing is the Ackermann steering. I'll just change the light direction so that we can see it. I believe the tires are visible right now from here, the front view of the tires. So if I steer, you can clearly see that the like inner wheel is steering less and the outer wheel is steering more. Same in the other way, like in the other direction. The inner wheel is steering more, the outer wheel is steering less. Yeah. Yes.
So before that, you could change the quality like high to ultra. Does that quality only has to do with visual rendering, or does it also refine your collision meshes? And
So currently it's only for visual rendering, but yeah, as you said, we can do that for two more things. One is the dynamics of the vehicle. So since you are working on reduced order models, we can have different dynamics models. So this is just a script. We can change the fidelity of the script. We can have multiple scripts which are now switched when you change the dynamics quality per se. So you can have as crude as a simulation that is basically just directly commanding like wheel torques without considering any driveline properties or any other vehicle dynamics properties. Or you can have really detailed dynamics models which are even more detailed than what we just showed in today's demonstration. And like similarly, we can do that for collision meshes as well. Another thing that I wanted to discuss is we are actually planning to have a co-simulation framework. So you can have the inbuilt simulation physics, but if you're not happy with them, you can just switch to MATLAB model, because Simulink models which are like already out there for vehicle dynamics, like any powertrain you want, IC engines, electric, hybrid electric, anything, and you can just directly update the transforms in the simulator. Just one final thing, which is the friction limit of the front and rear wheels, because it's a front wheel driven vehicle. Since it's a keyboard input, it is very clearly visible that
That's a cool shot.
if you see the front wheels and the rear wheels now, since we are hitting the throttle to the full and it's a front wheel driven vehicle, we expect the front wheels to just create a very high longitudinal slip, and that is actually what is even visible. And even with the handbrake, you can clearly see that if I hit the handbrake, the front wheel keeps spinning until the brake powers the vehicle down, and like if you still hit the throttle, the will spin in place.
So one thing you should say just to conclude today's meeting is Banta hai.
very nice.